Good morning, everyone. And today, welcome back to Trig, and today we're going to be talking about polar coordinates and graphs. Now, first of all, what do we mean by polar coordinates? You're used to seeing axes, and that makes sense, right? Axis and y-axis. And we got like a half axis involves the polar coordinates. That's the positive x-axis. And for the positive x-axis, that's what we measure our angle theta from. Positive coming this direction, negative going that direction. And now, to actually specify a point on the plane, okay, to specify a point on the plane, I will think of a radius r for our circle. When we talk about unit circles, well, multiply everything by r, and you got an r circle. And there's an R circle sitting out there somewhere. There's an R circle. Here's an R circle. And here's a little bit of its arc. Okay. Here's a bit of an arc on an R circle. It's going to meet a ray. That ray is specified by an angle theta. So the arc R circle meets the ray coming out at an angle theta. You get a point. And that point gets specified with polar coordinates r and theta. R for the R circle, theta for the ray where they intersect is 1 point. Right? Now let's compare that to like rectangular coordinates. Okay? So rectangular coordinates we get an intersection too, but they're perpendicular intersections, right? We have a particular x coordinate that defines a vertical line, a particular y coordinate that defines a horizontal line, and where the x coordinate meets the y coordinate is your point xy. It's really nice that there's lots of reasons why we want to use polar coordinates as well. But the nicest thing about rectangular coordinates is you have one x, one y, 1 point. All there is to it. With polar coordinates, we have some issues we have to resolve because there's going to be more than one way of specifying this point. Start with the fact that theta is not unique. Theta, because we're coming around circles, right? You can add 360 degrees or 2 pi as many times as you like. There's an infinite number of ways of writing theta that are equivalent to this cardinal angles. And there's another issue, we can reverse it. R is generally a length. We think of R as a length, and so we often think of it as being positive. But when I realign my thinking to let R be just a function value, we recognize R can have negative values. That's kind of like facing one direction, walking backwards. Okay? So if I'm looking one direction, if I'm looking this direction, okay? If I'm looking in this direction, and I walk backwards, 1, 2, 3, 4, 5, that would be R negative, R theta plus pi. And that would be another way of writing it. Or I can have negative R theta plus pi. It gives me the same coordinates. So that's the issue, and we'll worry about that in a second. First of all, let's just start off with a particular pair R and theta and see if we can figure out how to find them on a plane. So here's a couple of examples to get going. These are coordinates. The radius is 3, is 30 degrees. So when I go to graph this, I'll start off with a center. Okay? And now, best bet on this when you're trying to graph these, start off just by drawing a unit circle. Draw a unit circle. Okay? Now, from the unit circle, that's just to do a scale working off these. All right? From the unit circle, starting at the origin, out a ray corresponding to the angle from the positive x-axis, corresponding to this theta. So I'm looking at 30 degrees, I'll come out 30 degrees. There's my ray, 30 degrees. And now, in that direction, 30 degrees, scaled up with circle. R is 1, R is 2, R is 3. R is 1, R is 2, and here we have the point we're trying to plot. At this point, R is 3, and the coordinates, which again are unique, but one way of dividing it is with the coordinates 3, 30 degrees. So there were the steps when we did this. When we're trying to plot this, we find an origin, and that origin is called the pole, by the way. The origin is called the pole. Hence polar coordinates, okay? And then we drew a unit circle. We found an origin, we drew a unit circle, we drew an ray in the proper direction, and then we marked off the distance along that ray until we're at the radius. And that's how you plotted it. Let's do that again for a different point. 5, 7 pi over 12. And this one is obviously given in radians, so we're going to have to march up with that as well. Same idea though, okay? Start with your origin, draw a unit circle, just for scale. Now find 7 pi over 12. Now for you guys, it's often kind of like, I can't think in radians. But remember, if you're here at 0, then over here is 12 twelfths. I picked twelfths, and that gives me an idea. So here's 6 twelfths. And 7 twelfths is going to be 1/12 past that, like 15 degrees. Right there at 7 twelfths. Now I'm going to draw that ray. Coming up at 7 twelfths, and now I'm going to mark off R equals 1, R equals 2, 3, 4, 5. And there's my point. Radius 5, angle theta, 7 pi over 12. Okay? So that gives us a couple examples on how to graph these. So your steps on this: draw a pole, draw a unit circle, draw a ray running through the unit circle at that angle, mark off the distance on the ray, and go from there. As I said, polar coordinates aren't unique. For any particular radius and angle theta, theta has an infinite number of coterminal angles that represent the same direction. So I could talk about 30 degrees, and that's the same thing as 390 degrees, and it's the same thing as negative 330. 30 degrees and 390 degrees, and negative 330 degrees are all the same angle. And so this point at 330, yeah, that's the same as the point at add 360, 390 degrees. Subtract 360, negative 330 degrees. And we can add multiples of 360 all the way around. But there's another thing that we could do, which is also kind of and that's the reversal. Instead of marching, where's 30 degrees, guys? Let's take a look at this. Make sure that we see which way it is, okay? Here's 30 degrees. This direction, yes, that's 30 degrees. Okay? Exactly opposite that, this direction, is 30 plus 180, 210 degrees. Okay? That's 30 plus 180, 210 degrees. So I could look in the direction 30 degrees. I could be looking in this direction. And then march off 3 points, 3 steps. Or I could be looking in this direction 210 degrees and walk backwards. From r equals 0 to r equals -1, 1 step backwards. R equals -2. My pencil just decided that it wants to get a little extra juice. So we're going to give it 20 seconds, and hopefully that'll give us 5 minutes or so. That should be enough for right now. I can step backwards -2, getting myself here, or I can step back all the way to -3, in the 210 degree direction. So we can go forward to 330, or we can go backwards to -3, 210, and end up at the same spot. So as I said, and of course there's all the coterminals from there, -3 plus or minus 360 on the 210s. So let's take a look at this next example, doing the same thing with radians this time. Okay, here we go. I'm going to find alternative ways of writing this. Now, first of all, I can add multiples of 2 pi. Remember, if you're looking at this and you see fractions, just multiply the fraction by 1, 12 twelfths for 2 pi. You want to figure out what 2 pi is so you can add it elegantly as fractions? Start with a 2 pi and multiply it by 1 with your new fraction. That's 24 of those, right? What's 11 plus 24? What's 11 plus 24? Guys, what's 11 plus 24? I don't trust my arithmetic today. What's 11 plus 24? Oh, good, because I was going to say 25. Thank God. 11 plus 24 is 35. 35 pi over 12. There we go. What's 11 minus 24? Thank you, Daniel. Really, my head is in a fog. My arithmetic is not working today. 11 minus 24? See? Joshua is trying to be tricky. Trying to catch me. No, that's -13. Yeah, you betcha. Negative, right? There we go. I tried to get your own back from the other day, right? Yeah. Okay. Yeah, that's -13 pi over 12. Okay, that's one way of looking at it. Now, let's also look at the reversal. Instead of going +5 in the 11/12 pi direction, just so I have an idea what I'm looking at, let me just kind of like visualize that for myself. So here's my circle. Here's 0. There's 12 twelfths. Here's 11 twelfths. And the opposite direction is like what? -1/12, yeah? That's the -1/12 direction, right? So instead of marching 5 units in the 11/12 direction, I can mark -5 direct units in the -1/12 direction. Honestly, I was going to add 11 to 24 and get 25. God. There it is. So there we are. And so there are different present representations for these polar coordinates working with coterminal angles and this reversal of the direction on the radius r. Okay? Now, of course, we got polar coordinates and we've got rectangular coordinates. We should be able to move from one to the other. Yes? Because they're both specifying a point, you want to be able to translate then from one set of coordinates to the other. So let's do some exercises on that as soon as we got the theory. Now, polar to rectangular, that's no problem. You've done this before, right? We know already, because we did the r cis theta forms, right? We know already that if we're starting with a point on the unit circle, let me clean that up. If I'm starting with a point on the unit circle, we know its coordinates are cis theta or cosine theta sine theta. Let's call it cosine theta sine theta, right? Cos theta sine theta, right? And if I scale it up times r, I get r cosine theta, r sine theta. But it all comes down to the same thing, right? X is r cosine theta, y is r sine theta. Cosine is an x thing, sine is a y thing, scale times r. Okay. So that's easy. If you're trying to go from polar back to rectangular, it's just grab your calculator and go, or go from, if it's a principal angle, just work off the principal angles and you're there. Now, working the other direction, of course, is going to be, because life is never as nice as you want it to be, is going to work a little bit more complicated, but not that bad. The first thing is, let's go ahead and assume we want a positive r. And if we want a positive r, the answer is just use the Pythagorean theorem. We got a coordinate xy, we got coordinates xy, right? Here's a coordinates xy. The radius is going to be the sum of the squares, the square root. That's the r. Exactly the way you expect, right? Now, at the same time, what do you see? You are seeing rise over run from the origin of y over x. The tangent of the angle theta is y over x. Yeah, y over x, the slope, right? And so if you're trying to find the angle, your first thought is just arctangent y over x. Yeah, because tangent is a slope thing. Professor made sure that you would associate with that. Cosine is an x thing, sine is a y thing, tangent is a slope thing. So your first thought on this is just no problem, guys. You're looking for the angle, it's just arctan y over x. Done, right? Okay, look at this a little more carefully, and we see there's some issues that are going to show up. The first issue is, what if x is 0? If x is 0, you're still going to have an angle. Oof! You're not going to be able to calculate it like this, right? If x is 0, the tangent is infinite. Yeah? That means you're either going, and if it's actually a point not on the, I mean, the origin itself, the pole doesn't have any angle associated with the pole. They think of the pole as every direction at the same time with a radius of 0. So we have to handle the case where the x-coordinate is 0. Well, that's not that bad. If the x-coordinate is 0, well, that means that y has to be positive or negative, yeah? And if y is positive, that's the angle pi over 2, or 90 degrees. And if y is negative, the angle is negative pi over 2. So we can handle the spot where x is 0, that is, we're on the y-axis, fairly easily. But then there's another problem. That's the easy problem. So if x is 0, that means we're on the y-axis, and either we're up above, in which case the angle is 90 degrees, or we're below, and the angle is negative 90 degrees. But there's another issue. Arctangent only gives us 180 degrees of answers in your calculator. Remember, arctangent works with sine. Sine is a y thing. So if you look at the arctangent, its range, now here is where the fuzz hits me. Arctangent works like arcsine. Sine is a y thing, as in the range of the sine is a y thing. No. Yes. Sine of y, sine is a y thing. Okay? So the domain of the arctangent, so the range of the tangent is, well, the arctangent works with a sine, and it gives me y values back. But it's only going to give me 180 degrees worth of it. It only gives me answers in the first and fourth quadrant. What do we do if the answer is, if the actual angle, the point itself, was over here or here? What if it was in the second or third quadrant? Well, that's not too bad. If it's in the second or third quadrant, we'll just add 180 degrees. And that will take my calculator answer to the actual angle. Just add 180 degrees. And so we think right there, what does it mean to be in the second or third quadrant? That's when x is negative. If the x-coordinate is negative, the arctangent that comes out of your calculator is going to be off by 180 degrees, or pi radians. So to fix that, just add the pi back in. So there we go. Your happiest thing is when you're in the first quadrant. That's just arctangent y over x. Second happiest, you're in the fourth quadrant. Arctangent y over x. If you're in the second or third quadrants on the point, then you got to add 180 degrees to what your calculator tells you. So that's what you got to watch out for. So let's do some of the easy ones first. Polar to rectangular, only one answer. Favorite, 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 right? So in this case, let's find the x and y coordinates. This is polar, -5, 5 pi over 3. Pretty easy to see it's polar, right? X here is going to be -5 times the cosine of 5 pi over 3. Y is going to be -5 times the sine of 5 pi over 3. And we can actually know what that is because that's a principal angle, right? Let's take a look, see where 5 pi over 3 is. Here's my circle. I'm looking at thirds, so this is 0, that's 3/3. This is also 6/3, 5/3. 5/3 is not 6/3, it's not 3/3, it's 5/3. 4/3, 5/3, there's 5/3. And that's going to be the same thing as 60 degrees, pi over 3. And the cosine there is an x thing. Cosine there is an x thing, and that's negative 1/2 then. Negative 5 times 1/2. Not 1/2. Times negative 1/2. Yes? Cosine of pi over 3 is 1/2. Nope. What is the x-coordinate 5 pi over 3 there on the unit circle? Somebody tell me, because I'm obviously not thinking right. What's the x-coordinate here? Whoop. Let's try this with actually drawing instead of purpling. There we go. What's the x-coordinate right there, guys? On the unit circle. What's the x-coordinate? What's the x-coordinate over here? It's the same x-coordinate, right? People can hear me? The x-coordinate is not 1. No, it's not. X-coordinate 1 is over here. What's the x-coordinate here? 1/2 says Joshua. Joshua is correct. Yeah. And that's going to be the same x-coordinate 5 pi over 3. So this is negative 5 times 1/2. The y-coordinate, well, what's the y-coordinate pi over 3? Yes? Root 3 over 2. Yeah. You can just say root 3 over 2. A lot of students, when I'm seeing that, when I'm asking this question, they like just write this, SQRT 3 over 2. Like that. That's probably pretty good. If you want to get really, really fancy, okay, try option V. Try option V. Ooh. Yeah. That's option V. Ooh. Yeah. Okay. And what's the sine of pi over 3? Well, sine of pi over 3 is root 3 over 2, but it's the opposite on the other side, isn't it? It's the opposite. It's negative root 3 over 2. Negative root 3 over 2. So the coordinates I'm seeing are 5/2 and negative 5/2 and 5 root 3 over 2. Ooh. Joshua is on Windows and option V doesn't work for him. Is that why you're sad? That's right. On Mac is only for Macs. Yeah, well, SQRT looks cool too. Yeah, yeah, it's just as good. As a matter of fact, it's even better. SQRT is even better than option V. I keep on saying that. Eventually you'll be convinced, right? Okay. So the coordinates here, when we're done, and nicely the rectangular coordinates are unique, the point becomes negative 5/2 5 root 3 over 2. Yay! Squirt for the win, right? Yeah. Squirt 3. Patricia. Patricia. Patricia, answer the poll, please. Okay. Let me talk to Patricia. Patricia for a second because I've got something for her. I've got something for Patricia. Okay. Okay. There we go. Yeah. Okay, so there's it. Yeah, we've been trying to get a hold of Patricia so we can give her something. All right, there we go. That's good. Yeah. You do that for me, Patricia? All right? You do that for me? Okay. That's what everybody was trying to call you the other day. That's what it was about. Oh, thank you. And you got it? That's awesome. Thank you. That's great. Thank you. Okay. Ooh, man. Yeah, well, that's great. And it wasn't close. We'll see how that works. I'm finding my students on the phones, man. They're just losing connections like mad. I mean, I had one student in here right there was like having to rejoin 9, 10 times in an hour. I had a student yesterday had to rejoin 10 times. Or no, actually that was Tuesdays. Tuesday's lecture, I had a student had to rejoin 10 times using the phone. And like the laptop apparently is just, I don't know what's going on with the phones. I don't have the problem with my tablet, but there it is. Oh, I know. Well, on my tablet, I'm not really using 4G, whatever like that. I'm using my Wi-Fi on my tablet. Okay, so here we go, guys. Let's do one more polar. See how much we can knock out today. I've got you guys till 12:30, right? 12:30. Okay. And so here's my next example. Let's do this. X equals 8 cosine 2 pi over 3. Y equals 8 sine 2 pi over 3. Okay. And again, I got to figure out what the angle is on this, right? I got to figure out my thetas, my cosines and sines. Yeah. So let me figure this out. Pi over 3, that's 0. There's 3, 1, 2/3. And that point is going to undo. Actually, that point right there is going to have the same reference angle as the last one. Right? That's going to have the same reference angle as the last one, which is at 1/2 3 over 2, right? So in this case, x is going to be equal to cosine to half. Cosine is 1/2. And no, the cosine is negative 1/2, but the sine is still 3 over 2. There we go. So this is 8 times 1/2, 1/2. And this is 8 times root 3 over 2. There we go. So the xy coordinates corresponding to 8, 2 pi over 3 are going to be negative 4 and 4 root 3. There we go. And that's unique. That's unique. That's the only way to describe those coordinates. The other side around, well, let's work with these. This is giving rectangular coordinates. I want to come up with polar coordinates. Okay? And so let me just kind of sketch this in so you can see what's going on. Here's the point 0, negative 9. As soon as this thing decides that it wants to accept me. Okay, there's an issue because my pencil has run out of charge, and so I'm going to talk to you a little bit. Guys, look at this thing. 0, negative 9. Can you visualize where that's at? Draw that on a piece of paper right next to you. Hopefully everybody's keeping paper next to you, not just relying on the videos and my lecture notes. Who knows, maybe they are, I don't know. Yeah. 0, -9, yeah? Okay. And think about this. How far is that from the origin? This is a lot of work. How far is the origin? Between Q3 and it's called quadrantal angle. Yeah. You realize that's just straight down, yeah? How far is the point from the origin? It's called quadrantal. It's a quadrantal angle. Yeah. Yeah. In any case, yeah. But the first question I have is, how far is that point? It's 9 units away. That's R, guys. It's R. R is 9. Got it? Now it's straight down, right? What angle would take you down? What angle would take you straight down? 270? 270. That works. 270 degrees. Yeah. 270 degrees. So you know by inspection what the polar coordinates are. And sometimes you're going to be able to do that. Don't go bother with the arc and don't start with the other stuff right there. Just by inspection, you can see that this is not a color for answers. This is 9, 270 degrees by inspection. There are other positions that are just as easy to do by inspection. Let me give you a couple examples. 1-1. What's the angle of this one? You should be able to just visualize it. What's the angle? What's the angle in this one? 1-1. Visualize it. No, not 30. What is it? That's straight. I don't want to use the term because it involves the answer. Yeah. Look, yes, here it is. Start the origin. 1, 1. This direction, angle. Yes, Daniel. Yes, Daniel. That's 45 degrees. That's 45 degrees. And again, that's just by inspection. When you've done these enough, you recognize the length of that unit diagonal is √2 as well. And that's easy to work with, right? Just so there's some things that you can just do by inspection. And some things you need a little bit more to see that's by inspection. It's not that tough. Okay? So those you should be able to work off, right? So let's look at this next example, which is also going to be a principal, but we'll see that as we go along, right? Okay. 3√3, -3, okay? Yeah. Now, first question is, what's the length, guys? What's the length? To find the length, you can use the Pythagorean theorem. Okay? You can use the Pythagorean theorem to find the length. What's the length? Use the Pythagorean theorem. Somebody use the Pythagorean theorem, tell me what the length is. Come on, this isn't tough. You know how to use the Pythagorean theorem on X and Y, right? Square, square, add, square root. 6. Very good. Anthony. Thank you, Anthony. I want you to notice something here. Yeah. What I did is I saw the scalar 3 because I realized this is 3 times root 3 negative 1. Scalars are just going to scale. Either you're scaling radius or x or y. That's something for people who can see it. You can't see it. We're going to go straight back to the usual right there. R is x squared plus y squared, and the square root. 3 root 3 squared plus negative 3 squared is 9. 3 is 27 plus 9. 36 is 6. There's R. Now for the angle, it's the arctangent of negative 3 root 3 y over x. And that's the arctangent. Myself just a little bit more space here. Tangent negative root 3. And that's a principal thing. That's a principal. Let me do a quick sketch right here. I think of 1 skinny, 1 over root 3, fat, root 3, in the middle, 1 for the slopes, and negative, and the negative, and 1 over root 3 is 30 degrees, so negative 1 over root 3 is negative 30 degrees. But there's one thing I need to check. There's one thing I need to check before I do it. Okay? And that is to make sure that x was positive. So I'm in the first or second quadrant. Because if it was in the second or third quadrant, I have to add 180. Right? Yeah. There's a small slope and a big slope that you got to worry about. The small slope is 1 over root 3. The big slope is root 3. And the small slope goes with 30 degrees. And the big slope, the large slope, the steep slope, is 60 degrees. That's the root 3. This is 1 over root 3, so it's the 30. Okay? Right. And now, one last example, which I expect you all can do by inspection again, right? What's the length? What's the length, guys? How far is this from the origin? Yes? It's 1 unit straight down, yeah? And the angle? We just did this. What's the angle? No, that's not right. The length is 1, yeah? But where is this thing? Right there, yeah? 1 unit straight left, 180 degrees, yeah? Or pi. So those, if you got 0 on one of the coordinates, you should be able to just do it by inspection at a quick glance, right? Another little thing I should toss in here just as an extra example, something interesting. What's this in polar? What's the length? What's the angle? What's the length? If the angle is 0, yeah? The angle is 0, yeah? What's the length? Length is 5, yeah? On this one. This is 50. Degrees or radians, right? And so in radians especially, where there's no degrees measures, the coordinates along the positive x-axis are the same in rectangular and polar if you're using radians. That's kind of interesting little thing to check. Okay, I got bunches of stuff for today, and we're obviously not going to finish it. But we'll finish this much today, and then we'll come back and do graphs on Tuesday. And other material is just going to have to, what? That's week 16, though. I have faith. I also have a watch in front of me that says 17 minutes. And I know how long it takes to do these graphs. Nope, ain't gonna happen. That's okay. Well, wow. Really, 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 really want to do the roots, but you know, there it is. We're gonna do what we can. I don't know what to do. You know what I do know? I do know I don't have to do this. So let's go over here and do this instead. Don't have to do this. Yes, I do. No, I don't. Yes, I do. No, I don't. Yes, I do. Yes, I do. Okay. Graphs on Tuesday. And then I'm going to just show you mechanistically how to find roots of complex numbers. Just roots of unity. I think I can cut it just down to roots of unity and get you answers on that before we finish, and that will do it. Criminy. Okay, here we go, guys. We're going to translate these equations now. We're going to translate these equations from rectangular to polar. Now, the thing is, especially for functions, and that's the most important thing, you're used to seeing y as a function of x, right? I want to point that out, right? You're used to seeing y is a function of x, or y is equal to f of x. But you can just think of it as y of x, right? And I want to point out, guys, when we do angles in polar, it's r as a function of theta. Do you recognize? You'll have r as a function of theta. And you notice the difference here? In the rectangular coordinates, that is your dependent variable. But in polar, your first coordinate is the dependent variable. That's the way it's set up. Okay, so you can pay attention to that. That's kind of like a weird thing, but you get used to it fairly quickly. X squared plus y squared. We're going to translate that to polar. We're going to translate x squared plus y squared to polar. Yay us. Yay us. That's how easy it is. That's something you should recognize immediately. It just goes straight up to r squared. And now we're going to change up. Yeah, let's use up those 17 minutes. You're funny. You're a funny man, Joshua. Yeah. So, 2r cosine, no, not cosine, sine. 2r sine theta. Yeah? There is the polar equation. X squared plus y squared, you keep an eye out for that. And x and y are just r cosine or r sine. And this actually comes down to r is equal to 2 sine theta. Yeah. Which, if you had a little more experience with it, you recognize as a one-leaf rose. That's a one-leaf rose. That graphs out over here. Where? Sine 0 to 1. Yeah, here it is. There's the graph. It's a circle sitting above the plane. Okay, here we go. Let's try this one. X squared minus y squared. X squared minus y squared equals x plus 3y. Yeah. If it was x squared plus y squared, we'd be just like so happy, wouldn't we? But it's not, so we're going to just go ahead and do it, okay? I get r squared. No, I get r squared cosine squared theta minus r squared sine squared theta equals r cosine theta plus 3r sine theta equals r squared cc minus ss, right? cc minus ss. You see cc minus ss? Cos 2 theta. Equals r cos theta plus 3 sine theta. Kill an r. I get r equals cos theta plus 3 sine theta over cos 2 theta. Yeah. That's a one-leaf rose. And I want you guys to see it as a one-leaf rose when we look at those graphs later. This one is great. This one's great. This one is going to end up with a form that you're just not going to expect. I'm going to change this around. I'm going to change this one from polar back to rectangular again. And there's a trick for this. There's a trick for this. First of all, I'm going to write it as 1 equals 8 times 7 r cosine theta plus r sine theta. When you're translating from polar to rectangular, and you see cosines and sines, you want to turn them into r cosines and r sines, because then you get x's and y's out of it. Yeah. And so this is now 8 over 7x plus y. Yeah? And that gives me 7x plus y equals 8. All right? And that's a line. That thing right there, this is what a line looks like in polar coordinates. This is the general form of a line here, 7x plus y equals 8. Yeah? Okay. And you just don't recognize that's a circle. That also, but I think of a circle as a one-leaf rose. I'm going to stop the recording right now, and then I'm going to go over a little bit of what we're doing next time, so you have an idea of what's going to go on next Tuesday, okay?